Okay, we're going to solve some exponential equations that require logs. So we solved some exponential equations before that didn't require logs by just changing the bases to be the same thing and then setting the exponents equal, if you remember. But this isn't a case where I can do that because we have something that's base 11 and something that's a 67 and a 5 here. And this doesn't feel like I'm going to be able to change these to the same base. So I have to find some other strategy for this one. So I'm trying to get the x by itself because that's what it would be to solve, right? I'm trying to find the value of x that makes this statement true. And so in order to do that, I like to have the x on one side and everything else on the other side so that, we know the value of x that makes it true. So the first thing I would do here is actually subtract 5 from both sides. So what I'm going to do here is we're going to need some other information maybe to solve this one. But what we'll do is instead of going over a bunch of information at the beginning, when we hit a place where we need that extra information, we'll talk about it. And I actually think we're at one of those places here. So clearly you can see that 62 is not something I can change into 11s, make it 11 to the something. So this isn't really one where we can use that strategy that we've used before, okay? So let's talk about the idea that we are going to use. So over here, I'm just going to draw or write something else. Let's say log base 2 of 4 is equal to log base 2 of x. If I had something like this, hopefully you would agree with me that x must be equal to 4 here because everything else looks the same. So if you think about it the way we did our exponential equations how we were solving them before, we had something like this: 4 to the 3x is equal to 4 to the 2x minus 1. We said, oh, well, if these have the same base, then these exponents have to be the same, and we literally set those equal to each other and solve. This is the same idea. If we know that the base is 2 on both of these, and this thing is equal to the exponent that I have to raise 2 to get a 4, and this is equal to the exponent that I have to raise 2 to get an x, but we're saying that those exponents are the same, then basically we're saying that those values are the same. So it's the same thing we're saying here. We're saying, well, the base is the same, and we want this value to be the same, so we don't want the exponents to be the same. This one, we're saying the exponents are the same, and the base is the same, so that means that the value would also be the same. Okay, so they're kind of saying the same thing, right? We are understanding them, or we're understanding them the same way. We understand that this missing thing has to be the same thing that's over here, and that these two things have to be the same because everything else is the same about them, and so to be equal, then these things have to be equal, okay? So let's take a look at this. If I said 2 plus 5 is equal to 7, everybody would say, yeah, that's true. So what? What if I changed it to log base 2 of 2 plus 5 is equal to log base 2 of 7? Would that still be true? So doesn't this say log base 2 of 7 is equal to log base 2 of 7? So I don't think anybody could say that that wasn't true, right? Everyone feels that that's true. All right, I'm actually going to use that idea over here. This is the idea I'm going to use, that if this is true, then when I stick those values inside of a log with the same base, then it's true, because I could also say log of 2 plus 5 is equal to log of 7. I could also say log of a half 2 plus 5 is equal to log base a half of 7, right? All of these things, they're all true, or they're all equal, right? If this original statement was equal, then all of these are also equal. Does that make sense? All right, so the base that I'm going to use today, and there's different ways that you can approach these, but the base that I'm going to use today is this one. And do you remember what base it is if it's not listed? If there's no little number here, remember that means base 10. And we call him the common log, because base 10 is often the one that you're going to use in science, and you use it for lots and lots of different things. So we call him the common log. We kind of use it well, I guess we don't use it for, I was going to say scientific notation, but that's something a little bit different, okay? But this is, I'm going to use this idea here. You ready? Let's get to it. All right. So if these two things are the same, I'm going to claim that this, if I make a log and I put this thing inside, 11x minus 13, that still has to be equal to if I put this guy inside of a log. So I'm going to put him all inside of a log. This is still going to be equal. All right? I'm claiming that that's still equal. And for the same reason that we just saw, these are still equal. It makes sense. Okay? Now, why in the world would I want to stick a log in here and make this seem more complicated? Well, the reason is because I have all my log rules that are going to actually help me get this exponent or this a variable out of the exponent, because that's the problem. That's why I can't solve this right now, because the variable is in the exponent, right? But we do know something about logs. We know that log m to the n is equal to n log m, right? And if you don't know that, then you wanted to get out the video on properties of logs and take a look, okay? So let me rewrite this on a nice clean piece of paper because it's getting a little confusing. So let me make some nice big space and we'll put it right up here where you can see it. Okay, so this is where we are, and I'm going to use this property right here. So I'm going to bring that exponent down to the front. I'm going to say x minus 13 is equal to log 11. Okay, and that's equal to log 62. It's much easier to work on a chalkboard because you can just erase your mistakes instead. All right. Now, the goal is still the same. I'm still trying to get x by itself. That's what I'm trying to do. I'm trying to solve. Now, there's something that we have to keep in mind, that log 62, that says it's just what do I raise 10 to get a 62? So it's whatever this number is. I don't know what number it is, but it's a number. It's some wacky number, but it's just a number. And this is the same thing. This one says 10 is something, if I raise 10 to something, I'll get an 11. So that's what this one is. But again, just a number. I don't know what it is. My calculator knows what it is. But it's just a number. It's just like if you leave something in terms of pi. We all know that pi is a number, and we know that it's approximately 3.14, but it's actually got a lot more numbers. We don't know what all those numbers are. Just like these ones, I don't really know exactly what that number is, but getting to here is good enough for me as long as there's no x's in them. I'm going to show you how to get the decimal approximation also in case you need to do that in your science class, or if it's a multiple choice test or something and they've given you the decimal approximation. All right, so how am I going to get this x by itself? Now, if you've looked at some of these that we've done in class where we had these two things multiplied together, but the x is on the inside of the parentheses that I'm trying to, solve for, we could distribute. That is definitely an option, but I'm actually not going to do that. I'm going to just divide by log 11. And why? Because that cancels this one out. And that puts me in a position where now it's kind of easy to solve for x. This is log 62 over log 11. And the only thing that I have to do here is add a 13. So x is equal to log 62 over log 11 plus 13. Now for me, if we have an open response situation, that answer is perfectly okay with me. This is what we would call the exact answer. But we could find the decimal approximation. So this is the exact answer. That's the actual value that this x is equal to. Now, if I put it into my calculator, I'm only going to get an approximation because I'm going to have to round some decimals. And everybody knows that once you round, then you are making the number not exact anymore. Okay? So what I'm going to do is I'm going to hit this log button here. You see it? I'm going to do log 62. So my calculator only does two bases. It does log base 10 and log base e, which we'll talk about in another video. And that's why I chose to use base 10. I chose base 10 for this one on purpose because that one I knew my calculator could find out for me. So from here, I did this division, and now the last thing that I have to do is add 13. And we see that my decimal approximation is 14.7211. This is my approximation. So if they ask for an exact answer, they want something with logs still in it. And if they ask for an approximation, a decimal approximation, sometimes they'll tell you what to round it to. If they don't tell you what to round it to, I like to keep at least 4 decimal places. You can keep more if you like, but at least 4, because that's, probably accurate enough for anything we're doing in math class. I mean, if we were sending someone to the moon and doing the calculations for that as an astronaut or something, maybe we would need a lot more decimal places, but probably in class, 4 decimal places is good enough. All right. So we'll do one more so we can kind of get our brain wrapped around this. And then in my next video, maybe I'll do it in the next video, I'll show you instead of tacking it onto this one, because I know after a few minutes it's hard to pay attention. In my next video, I'll show you how to do it without using base 10, but using the idea of inverse functions, all right? So let's take a look at this one. We're going to do this one the same way. We're going to use base 10 or base E, but since we haven't really talked about base E too much, let's do base 10 instead. All right, my goal here is the same. If I'm going to solve this, I'm trying to get the x by itself. So I'm trying to get everything that's not an x away from the x. And the 5 is a good candidate to get rid of, right? So we're going to divide this side by 5. Over here, of course, the 5's cancel, and over here, is that a 15? It goes 1 with a 2, no, 14. I hope that's right. 7 is 14 times 5, 70. I hope so. All right. So now what we have to do here is use our fancy log trick. So we're going to say that if this is true, if I stick a log in front of each of these, it's still equal. It's not the same equation anymore, but it's still equal. Okay? If these two things are equal, then this is also going to be equal. So we call this, I call it log both sides. You'll hear that sometimes, log both sides. So I logged both sides. Now I'm going to use my exponent rules, and this is why we changed it to a log, so that I can move this thing down here. So I'm going to say x plus 3, log 4 is what's left, is equal to log 14. Make sure you have parentheses around this if it's more than one term, because if it's not, it would say, if I write x plus 3 log 4, that does not equal x plus 3 log 4, right? There's a big difference between these two things, because this says x plus 3 times this, and this says log times both of these. So this would mean distribution, right? But this one does not. So make sure that you're using your parentheses or you're getting the wrong answer, okay? So from here again, what am I going to do? I'm going to get rid of the things that are around the x by using my opposite operation. So basically I'm solving the equation just like I would any other time. I don't know why I crossed this side out, but this side cancels. This side I don't cancel out. I don't know why I crossed it out. Got carried away talking. All right, and the last thing I got to do is subtract 3 from both sides. Now again, for me, this answer is perfectly fine. I love it. I would leave it. I'm happy with it. If you want to type it into your calculator, to get a decimal approximation, you can, but I will probably ask for exact answers, so I want you to leave it in terms of log if I'm writing the test, okay? So see if you can think about the ideas that we talked about here and see why they make sense, and try them out on some of the questions that you have for your homework and see how it goes.